Hi, hello there again. It's AWOL Geordie back here with another little bit of a maths exercise. I made a YouTube video like a few years back and they don't get many views, but it's not for that. But the most viewed one was the one about e to the pi I equals -1. And there was a question in the comments saying, like, how do you get that formula? I just stated it with a brief explanation. So today I'd like to go into a little bit more depth about it. And it comes from a thing called the Taylor series, a mathematical entity. There was a man called Brooke Taylor. He was an Englishman, and in 1715 he come up with this beautiful equation here, which is an infinite sum of a load of polynomial terms. So what this does, it can represent any function as a sum of increasing polynomials, right? It's pretty cool. Now, if you do engineering at university, you should encounter this, but when I was back in my naval apprenticeship, I didn't do this, so I thought I'd take a bit of a look at it now. It's quite interesting. So we've got this thing called the Taylor series that can represent any function. If we use the more terms we use, the more accurate that representation is. Okay, so what I want to do is just plug in the values for, I want to represent e to the power x as an infinite sum of polynomial terms. And then I want to do sine x and then cosine of x. Now the first term is just the function itself calculated at a value a. Now I'm going to choose a to be 0 to keep things simple. And so that's quite straightforward. Now the second term is the first derivative, and again we're going to calculate what that is, the value of that when a is 0. Okay. The third term is the second derivative calculated at 0, and we get an x squared at the end of it, and divided by 2 factorial. So you can see these denominators just increase: 1 factorial, 2 factorial, 3 factorial, 4 factorial. You can see the derivatives increase, the first derivative, second derivative, third derivative, and the x to the x minus a, well, a is 0 for me for this case. So that'll just be x. And this is x power 1, x squared, x cubed, x to the power 4, etc., etc. So you can see there's a kind of pattern there. Now, the next thing I want to do then, to calculate them terms I was talking about, is the first one I'll do the cosine of x. So the f of x is cosine of x. Well, the first derivative is minus sine x. I'm just going to write them all down so it makes them easy when I work out the Taylor series. The second derivative minus cos x back to sine x, and just keep going. This will just cycle through and loops of 4. The same for the sine of x. I'm going to calculate the derivative, the second derivative, the third derivative, the fourth derivative, and on and on and on. And the last one is e to the power x. Now, the good thing about that is that e to the power x, the derivative is the same as the original function, so the derivatives is just e to the x. So that's lovely. So let's take a look at e to the x. Now if I do plug e to the x in there, and the x will be 0, e to the power 0 is 1. So I can put that first term in there. Lovely. Now the next one, the derivative, the first derivative of e to the x is e to the x. Plug 0 in again, I get 1, and 1 divided by 1 factorial is all 1. A is 0, so this just be the second term becomes just x. Lovely. Now let's look at the third term. It's the second derivative. Well, we know it's e to the x because I looked at that before. E to the power 0 is 1, so I'm going to have 1 divided by 2 factorial x squared. Or just x squared over 2 factorial, and that's there. Now if you carried on, you can see the pattern developing already, and it's just an infinite sum. Now the more terms I add to this, the more accurate it'll represent e to the power x. So it's pretty cool. So that's that one done. It's quite a famous Taylor series and quite easy to do. Now the next one I want to look at, I want to get the Taylor series for the cosine of x. Now, here's all my derivatives of that one. Now the cosine of x for this one, well, the a is 0 again, so the cosine of 0 is 1. So that's my 1 down there. Now the next one, the first derivative is minus sine x. Well, that's going to be minus sine 0, which is 0. So this whole term disappears. Now the second derivative is back to minus cosine x. So I'm back up to here. I've got minus cosine of 0 will give me minus 1. So that's going to be minus x squared over 2 factorial. And that's exactly what I get. Now if I carry this on, I'll get 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial, and on and on and on with these signs alternating each time. So it's kind of we're getting the even powers, you know, that'll be like x to the power 0. So we're getting the even powers of x for cosine, and cosine is an even function, so that kind of makes sense. Now let's go to sine. Let's look at sine x. Now, first term is sine x. The sine of 0 is 0, so that term down here, I've just left it blank. The next one is the derivative. So the derivative of sine x is cos x. And cos to the 0 is 1. So this is going to give us 1x, which is just x, and there it is there. Okay, so it's below that one. Now, the next term is minus sine x. Well, again, it's going to plug 0 in, so this whole term will just become 0. And if you carry that on, you'll end up with, it's kind of alternating terms with cos x. We end up with, again, with an alternating plus, minus and plus, and the powers this time are odd, which kind of makes sense given that sine x is an odd function. Okay. So what have I just done then? I've just worked out the Taylor series for e to the x, the cosine of x, and the sine of x. That's all very good. I've done that, so when we do the next steps, we can see, we can relate back to where we're coming from, okay? So the next thing I want to do is start to get into the complex number side of things. So as I said at the beginning, e to the pi I equals minus 1. Now I'm going to get to that eventually, but first, instead of having e to the power x, I'm going to put a coefficient of x in there of I. Okay, and that means I'm going to redo the Taylor series. I had it up there before, but every time I see an x this time, I'm going to put an ix. Okay, and I end up with that. Now, you should know from your studies on complex numbers, I get I squared is minus 1. So these two terms won't change, but this term, because of that I squared, it will become minus x squared over 2 factorial. Now look at this term, I cubed will give me minus I. So I'm going to end up with minus I x cubed over 3 factorial. And likewise, I to the power 4, if you've done your rotations on the Argand diagram, you should know that that just goes to 1. Okay, that changes to 1, so I'm going to have plus x to the power 4 over 4 factorial. And then I to the power 5, well that is just I, so that's going to give me another positive term. Now you'll notice we've got positive, positive, negative, negative, positive, positive, and it's going to carry on like that, negative, negative, positive, and positive. So what was the point of that? Well, if I take all the terms that don't have an I, like 1 doesn't, this does, so I ignore it. No I, let's write it down. No I, let's write it down. And look, that's exactly what the cosine of x was from before. Exactly the same. Okay. Now take each term with an I, starting with this one. Bang. This one. Minus I x cubed over 3 factorial. And this one. plus x5 over I factorial. Now you'll notice in both cases the signs alternate again. And if I take the I outside these brackets, if I factor the I out, I get this bit inside the brackets. And what's that? Well, that's sine x. We did it before. It's exactly the same. And I remember with my sine x, but this time it's multiplied by I. So I want to have I sine x. So I can see e to the power ix is going to give me cosine of x plus I sine x. Right? And that's exactly what a complex number is. If I have a unit vector on the complex plane with some angle x there, this side will be cosine x and this side will be, or it's on the imaginary axis, it's going to be I sine x. And that's that. Now I've just shown on the last piece of paper that this is equal to e to the power ix. And this provides us a lovely way of adding, well, multiplying and dividing complex numbers in a much easier fashion. Now that comes in quite handy when we're doing phase shifts through capacitors and inductors in electronic engineering, which is my background. And that's exactly where it comes from. It comes from the Taylor series. Now, just to look at Euler's identity, if I swap x for pi radians, I'm going to have e to the I pi. Everywhere I see an x, I swap it for a pi. And I work out each term. Now, the sine of pi is 0. And the cos of pi, well, that's -1, halfway through the cycle. So I get e to the I pi equals -1. And that's a lovely equation known as Euler's identity because it's got all the cool numbers of maths in it. It's got e, the exponential number. It's got, which represents growth and everything. It's got pi, which is all to do with circles, and it's got I, which is the square root of -1, which gives us all our complex numbers. And of course, we've got -1 on the other side. So that's it. Lovely. I hope you got something out of that. I like to go over things again and again and again just to see that I understand them more clearly. So I hope you got something out of that. Thanks very much. Bye.